Hi everyone. Thanks for tuning in and pardoning my absence today while I'm at this off-site meeting. Today we're going to start a pretty extended discussion of taking this notion of transactions and moving out of the single machine phase and into a distributed situation where we've got many machines working together to make some transactions happen. So remember last class, we started talking about transactions, and specifically, we were looking at the different maybe kinds of properties that we wanted to assure when we're doing transactions. So we looked at this motivating scenario where we're making a transaction which was transferring money. We're transferring money from some account to another. And maybe one of the first issues that we looked at was the issue of atomicity. And that was about making sure that there were no half measures here. The transaction either happened entirely or it didn't happen at all. So there wouldn't be any situation wherein we were able to deduct money from one account but not add the money to the other account. None of that. The transaction had to be atomic. We talked about the other properties. Had these acid properties, where the C was consistency, the same kind of consistency we've been talking about mostly. We're talking about serializability as something kind of a little bit more than sequential consistency, but less than linearizability. I was isolation, which was that we'd say each one of these transactions, even if they occurred concurrently, it would appear as if they were happening independently. And the D was for durability, which was that once these transactions occurred and they were committed, they couldn't be undone. We'd have this notion of fault tolerance. We talked about two key techniques that could be used when we built a transaction processing system to get these properties. We broke them up. We talked about atomicity and isolation in one context, and we talked about consistency and durability maybe in the other one. The first technique that we talked about was two-phase locking, which was our simple solution for isolation. Remember that in two-phase locking, we split all of our locks into two key phases. The first was acquiring locks, and the really key important thing there was that we need to be acquiring all of the locks that we could possibly be using, because once we finish acquiring locks and we start doing our work, we can't get more. And then in the second phase, we release the locks. So there's no notion of being able to acquire more locks after we start to release them. At the beginning, we acquire, and then we might do some work, and then we release. There's no ability to release some lock in the middle. And really the key important reason why we wanted that was that by using this two-phase locking, we can ensure that our transactions are serializable. So just as a refresher, what serializability meant. With serializability, we said if we have two transactions and both of those transactions are accessing some shared variables, in this case we have some variable A and some variable B, if we're going to have serializability, then it's almost like we're getting sequential consistency across multiple variables. And that's to say that either all of them happen before the other or none of them do. So either T happens before T prime, and T accesses A and T accesses B, and then T prime touches those two, or T prime happens first. What would not be allowed is for one transaction to read some of its values, and the other transaction to read some of the same values, and then to have the other values happen later. So this is a violation of two-phase locking and can't happen because, as we discussed, for transaction T here, the blue one, to access A, it could only access A if it was able to acquire its locks, and it needs to lock A and B. So for it to have gotten this before T prime did B, T prime must have released its lock on A to allow T to get the lock on A. But with two-phase locking, that's not allowed, so hence we will end up with serializability. The other key topic that we discussed with regard to transactions was fault recovery. So that was assuming that eventually something bad probably is going to happen. Maybe our machine will crash, maybe our program will crash, we'll run out of memory. We need to come up with some way to recover the transaction state. And our goal was kind of two-pronged. First, we wanted to make sure, perhaps most importantly, that if there were transactions that were committed, we needed to make sure that those transactions were not lost. And then for any other transactions that were in process, those transactions either had to continue where they were left off or they had to be aborted. And what was tricky there was that if some transaction were in the middle of happening and not committed, maybe some effects of that transaction could be visible. But we needed to be able to abort that when we recovered. So our high-level plan, we talked about this write-ahead logging strategy, where before anything was done on the machine, we would write to disk what we were about to do. And then this would allow us to recover, after we recover from the crash, we can recover our transaction state by going through that log entry by entry and reapplying or aborting each one of those actions. So today we're going to really dive a lot deeper onto this notion of fault tolerance, and we're going to be discussing fault tolerance in a distributed sense finally, specifically in the context of transactions. More broadly, what we're talking about today are transactions and even this bigger notion of agreement in distributed systems. So a few reminders before we get into this. Homework 3, as I'm sure you all have really realized by now, we're in the final days. It's due on Thursday at 11 p.m. We did that extension to give you a little bit more time to make sure you could get to my office hours on Wednesday by extending to 11 p.m. That will also allow you to attend the TA office hours on Friday and have that 10% penalty. I also wanted to draw your attention to a study opportunity where you can help improve software engineering by participating in software engineering research. Another one of the computer science professors, Professor Latoza, is conducting a study on different kinds of design rules and how programmers author these design rules or follow these design rules. It's an interesting little study. It just takes a few hours. If you're interested, you can follow this link. You could be paid $40 for participating. All right, so agreement. Before we get into distributed transactions, let's step back and generalize a little bit. So maybe a core issue with doing a distributed transaction is we're going to have multiple machines, and each one is going to have some role in this transaction, that maybe they're debiting money or crediting money. And each one is going to have to give a go, no-go, like, yeah, I can do this transaction, or yeah, I can do this transaction, or no, I cannot do this transaction. And collectively, among the three of these machines, even if they all have different desires, like maybe green was a better choice, yes, yes, and no, as a whole from the system, they all need to come together and agree on what happens. Like, we can't just have two machines who think that the transaction was committed and one think that it was aborted. So this is this notion of agreement. So in distributed systems, we might have these multiple nodes that are working together in some protocol, and we need to get them all to come together to agree that some object has some state. So in the context of transactions, that might be whether this transaction should be committed or not, or whether it was ever committed successfully or not. But more broadly, we might have some shared variables. We've seen in the context of multi-threading that we can have some variable like X and then have multiple CPUs. And we had, I guess the CPUs had little legs on them. That's how you know it's a CPU. And like maybe there were some weirdnesses with caches and volatile variables, but generally we said that if this variable x was 5 and each CPU looked at it, they should hopefully see the value 5. And even if we'd say, well, maybe you could see an old value, there were still these bounds. The thing that you saw had to be consistent for some definition of consistent. Similarly, we might have distributed systems that have locks, like in your homework 3, where we have just a single central machine that's in charge of keeping track of who has locks, but maybe we all need to come together to agree who has a lock or not. So this is going to be very recurring, having multiple nodes coming to agree on some specific state. So really, most distributed systems problems can be reduced to this one. Even though we might have multiple machines, and each one of the machines might have different views of data and different views of the world. I've got machine 1 over here, I've got an orange machine over here. These machines are different, but each of these machines that have the same object need to apply all updates to that object in the same order. That's our consistency principle, right? If we're going to be having some shared data, let's put our x equals 5. And I've got these two machines, they still need to be seeing this same object and seeing updates to that object in the same order. And all nodes that are involved in a transaction must either commit or abort. They're part of that transaction. That's the atomicity. So this was really easy, or relatively easy. We were able to discuss this in the context of just a few lectures before going distributed. So when we had these multiple programs, multiple threads, multiple processes running on a single computer, yeah, we had this weird cache coherence thing where we'd have the shared variable and we have to make sure everyone sees it, and maybe we use the word volatile, but that was that. But now that we're in this distributed setting, we need to be able to consider the fact that different nodes might restart or die or be arbitrarily slow. So we have this red machine here, it might just go away. And there's this network between the two also, and the network could be slower, the network could be unreliable also. It might start dropping packets. And that was, we had discussed before, this is where we risk having that split brain because we don't have the shared fate. So for different kinds of agreement algorithms, there are two kinds of properties that we want to be able to show, just like we showed for mutual exclusion. Mutual exclusion, we talked about both these safety properties and also liveness properties. So we do the same for agreement. So the safety property for an agreement protocol is that all nodes will eventually agree on the same value, and that value was proposed by one of the nodes. If we have two machines, we have our variable x, which is 5. So for safety, eventually this machine will see x equals 5, and this one will see x equals 5 as well. The fact that it had to be proposed by some node maybe comes into play in different kinds of more complex voting style applications of agreement, but it's just saying that this value x equals 5 was not made up. So either this machine or this machine wanted it to be 5. And then the liveness properties have to do with fault tolerance and availability. So we want to put some bound n so that as long as less than n nodes crash, our system will still be able to reach agreement and still be able to function. Okay, so this is agreement at the really high level. And we're going to shift gears a little bit and focus just on distributed transactions for the rest of the lecture. We'll explode back up to agreement overall next lecture, but safety and liveness properties, we're going to be talking about those in terms of distributed transactions today. All right. So how do we end up with distributed transactions? Well, it's probably not that difficult to imagine a scenario where we have a transaction maybe similar or exactly the same as our typical example that we saw last class, where we're doing a bank balance transfer. Now, In the hypothetical scenario where we're doing a transfer within our own bank, well, probably there's still multiple machines, but we could kind of wave our hands and say that this could all happen on a single computer. But if we're transferring money between different banks, then probably we'll end up having a distributed transaction where we're doing some addition in one place and a subtraction in another place. So we want to do this transaction. We want to transfer money from Barney at Goliath National Bank to Mortimer at Duke and Duke Bank. We want to transfer the amount of $1, and we'll start off with each bank account having $10,000. So we're starting out a transaction, and this transaction might start out at Goliath National Bank, but it'll involve both banks, and they'll communicate over this cloud. I have this transaction called transfer money, which is going to add $1 to Mortimer's account and remove $1 from Barney's account. Now, at the same time, we might have other transactions, and this transaction is going to involve both banks. There could be another one that gets started, say, on the other side of this pond that is maybe auditing records. This transaction is going to read the current balance of both Mortimer and Barney, and then print out what their balances are. Now, what could we hope, and what do we want, or think maybe the best thing could be if both of these actions happen at once? So take a moment and think about what possible values we could have or should have for temp 1 and temp 2. Okay, so hopefully there should be only 2 valid options that we want to see, although maybe others could happen if we implement this thing wrong. So hopefully either when the second transaction starts up, we'll see either 10,000 printed twice because the transaction hasn't occurred yet, or we'll see 10,001 and 9,999 because the transfer should be atomic. There should be no ability for this other transaction to observe an intermediate value where maybe one of them has 10,001 and the other has 10,000. If we saw that, then we printed money somehow, and while we like printing money, probably will come back to bite us. So we want to have our transaction be distributed, but still we want all of our fun transaction acid properties, especially atomicity. So why is this wrong? And why is this hard? And what can go wrong and give us these intermediate values? We might have the same kind of issue that we expected last class and talked about with our two-phase locking, where maybe these two transactions could be interleaved in some way, where part of one transaction ran and then another one saw the intermediate value. So we think we can probably solve this if we have some two-phase locking that we can do and have these shared locks. That'll probably solve that one. But there are going to be other more interesting kinds of failures that we're going to start seeing now that we're in this distributed scenario. Like maybe what happened was there was a server failure or the network failed, and maybe it was on either end. Maybe this transaction over here that was transferring the money was able to run the first step, and then it crashed here, and this never ran. So if that happened and that was crashed, what happens with this transaction? It's still going to be running, but we talked about this recovery protocol where after this guy over here, after he reboots, he can look at its log and say, aha, I started doing this thing where I gave Mortimer money, but I need to reverse it now. Let's reverse it now. But we can't, do we have to wait around for the bank to come back up to do that? I don't know. We're going to have to solve that one. Plus, where are these accounts and do they exist and do they have money? Like, there's some validation issue that's probably going to happen here also. So, of course, we're going to solve some of these problems using transactions. And then we're going to make more problems because then we need to explain how the transaction system works. So we'll use our same notion of transactions where we're going to wrap each transaction in some sort of generic begin transaction, end transaction block. So our client will tell the transaction system where to end or start the transaction, and then the transaction system will arrange these transactions in some way to ensure that those nice ACID properties exist. So our focus today is how we build the system that will take this transaction and this transaction and execute them both concurrently at this bank and this bank, separated by this cloud network in the middle. So we're going to focus much more on how to abort rather than how to commit, because far more things can go wrong than can go right, unfortunately, in a transaction. If a transaction goes right, then we commit it and everything is easy. Where we're going to see all of these nasty corner cases is what happens when things go wrong. For instance, if I have two transactions that are running and one has to abort, it needs to be able to undo any of its modifications that it started doing in the middle. And some of those aborts might be voluntary, like the transaction might just fail. Like if we made this transfer and said, I want to transfer money from Mortimer to Barney, and we started doing that, but then we found out we actually don't have Mortimer's account on file. Like we just can't do it. We have to abort. We still had those kinds of situations in a single machine transaction processor. But now we're also even going to see aborts coming from failure. Like if a server crashes, or if some part of the network code becomes unavailable. We might also start seeing cases with more nodes where the system might have some deadlock and need to abort. So we're going to be dealing a lot with aborts today. There are going to be two big components of how we implement distributed transactions, just like the non-distributed ones. First, considering concurrency control. Concurrency control, we're going to just say we will implement the same as in non-distributed transactions. We will use two-phase locking and assume the existence of a lock server that can manage our locks. But then we also need to manage this atomic commit thing to make sure that all of these nasty things that happen when and if things go wrong, we need to be able to undo a transaction. Right. So our system model for any and all of our distributed transaction systems will include a designated coordinator and at least one, probably at least two really, participants. So the coordinator is really any node. It just has to be one that is pre-agreed upon, that all of the participants agree that this guy's the coordinator. The coordinator is primarily responsible for assigning this unique transaction ID and deciding globally and unique and for sure whether we are going to commit or abort. So we said at the end of last class, as a little teaser, that here is a simple protocol, doesn't quite get there, for handling these commits. So we have our transaction coordinator shown at the top, and we have some participants at the bottom. In the simple naive protocol, the coordinator might just repeat out requesting for nodes to commit, and the nodes will respond back saying yes or no whether they can or cannot commit. In this really simple protocol that doesn't have much back and forth, we have a problem, which is that it only works if everybody says yes, right? If everyone is very cheery and the coordinator shouts down, would you like to commit? And this guy says yes, and this guy says yes, and this guy says yes also, then everything's all right because we're done. But if one machine says, no, I can't commit, if that's the end of our protocol, we have no way of reversing things. So this naive protocol where we just have a coordinator that says it's time to commit and our participants acknowledge that it's okay and they have committed isn't going to work. So we need to have some way to manage when a participant doesn't want to commit and informing all of the other participants that we need to do the support thing. All right. So if the phase one was naive, then maybe if we made this a two-phase thing, it could be less naive. So the key idea in two-phase commit is that we're going to separate this process of deciding for globally the entire system, like not just one machine, but overall deciding what the final outcome is. We're going to separate this committing into two steps. In the first step, which is going to be voting, each participant is going to prepare to do their commit and vote saying if I will or will not be able to commit. They're not going to actually do the commit. They're just going to prepare all of the resources that they need, get the locks that they need, check data to make sure that it's valid. Will I be able to commit? After voting succeeds, every participant will either commit or abort. So we're going to take all of these votes in from each one of the participants, tally them up. If anyone said abort, we abort, otherwise we commit. And we're going to assume, pretty much for the rest of the class, that we're going to have multiple nodes that are communicating over some sort of magic RPC that exists. So in this case, we're going to say that the participants are talking to the coordinator. How are they doing that? They have some RPC that we set up. So what does this look like? Let's step it through. To start out the process, we'd say to the coordinator, let's make a new transaction. And now the coordinator is going to ask every single participant, can you commit this transaction? And each participant has to do all of its preparation to be able to commit before it's allowed to say to the coordinator, yeah, I can do that. And one of the steps there, of course, we're going to see as we unpack this, will be saving some information about this transaction to disk so that later on we can recover it. Something really important. If a participant has answered yes to say, I would like to commit, I'm able to commit, they cannot change their mind. There is no way for them to ever abort under any circumstances after they vote to say yes, unless the coordinator tells them to. So the outcome of this transaction, of whether the participant should or should not commit or abort, is really going to be unknown until the coordinator hears back all of these votes and issues out its fiat ruling to all of the other participants, do the abort or do the commit. So let's look at this in terms of an event sequence. We'll look at just a case with a single coordinator and a single participant. Of course, it probably makes more sense if you have one coordinator and multiple participants, because just a single participant isn't really competing with someone else to vote. So we start out, and we've started a transaction, but we haven't done any voting yet. We haven't started the protocol yet. So both the coordinator and the participant are prepared, but they're not sure what's happening. So the coordinator asks the participant, can you commit? If the participant has everything they need in order to be able to commit, if they have their locks, if they've got their resources and their validation, they'll respond back saying yes. During this entire time period, though, while the participant is waiting to hear back, they have no idea what the outcome of the transaction is yet, right? Just because they voted yes doesn't mean whether the transaction has been committed or not. Once the coordinator receives all of those votes, in this case just one, as long as nobody voted to abort, which nobody did, we'll commit. And then we broadcast that message to all of the participants to say, all right, let's commit. Only at this phase is the participant truly done, that it knows that it's committed. And then finally we're done. That's our transaction. So let's step back to our example. We had this transaction where we wanted to transfer money between these two accounts at these two banks. And we want to have those two at least key requirements of atomicity and serializability. Plus the other I and D properties, but as we kind of discussed a little bit last class, we're going to get isolation when we get concurrency control, and we're going to get durability and atomicity together too. So for simplicity, we're going to assume that this transfer is marked by the call to this begin method, and will be ending with this call to this commit method. Including will be then, some transfer of money. So we have these two participants, these two banks, and we have a coordinator also. So again, the coordinator is maybe one of those banks, has just by default we said, well, alphabetically whoever comes first should be the coordinator, or maybe it's totally a third party like some sort of bank clearinghouse. So we run through our transaction code and everything is still isolated. Maybe we did some locks, we did everything. We get to the commit method, we call transaction.commit. At this point, both of the participants have to pause. They don't know whether the transaction can be committed or not. So the coordinator is going to start this out for us now, and it'll send these prepare messages to each of the participants saying, get ready to commit and let me know if you're able to. Now, if we can commit, we're going to make sure that we have our lock still, and then we vote yes to say, yes, let's commit. And those responses go back to the transaction coordinator. Now, as long as everyone voted yes to commit, then the outcome is commit, and otherwise it's abort. And then once the outcome is known, the outcome is broadcast to all of the participants. This is the entirety of the two-phase commit protocol, as long as we consider there are no failures. So how does this do in terms of our original properties that we wanted to get? So recall that we had two classes of properties we were interested in. We were interested in those safety properties, which was making sure that all of the nodes would agree on the same value. And we're interested in liveness properties, which was that as long as less than n nodes crashed, the system should still work. So as we've presented it so far, two-phase commit is going to guarantee safety because no participant can proceed with the commit unless they hear back from the coordinator. We got to step in to look a little bit closer at the liveness ones though. But for that argument of safety, let's just come back to this visual and see that at each participant, we don't know the outcome of the transaction until we hear it back from the coordinator. The participant can be totally just stuck for this entire duration here, waiting to find out whether the transaction can or cannot be committed. As long as the coordinator only says commit, as long as both participants said commit, then we have our safety property, hopefully pretty straightforward. So how do we get these liveness properties though, and how do we try to recover these transactions if we crash? So again, we have similar goals to before. If we have a transaction that was committed, it must not be lost. And if we had some transaction that was in progress, we need to be able to abort it or continue where it was. So first, we're going to lay out some various failure modes. We're going to talk about systematically, for each one of those things that could break, what happens if it breaks? And maybe think about some intuitions for solutions. And then we're going to formalize a policy to see how, in this two-phase commit protocol, we can do recovery and fault tolerance. So let's start off with an example where our coordinator broadcasts its prepare message to each one of the participants, and each participant responds back. In this case, maybe both responds back saying yes. But now at this stage in the protocol, before anything else happens, one of the machines crashes. One of the participants crashes. And then the protocol continues. So in this example, we see a participant that crashed after voting yes to commit. So let's think about what things could go wrong here and how do we need to tolerate this. So this participant did vote yes. So our key rule was that if you ever voted yes to say the transaction should go through, the only way that you can abort is if you hear this abort message. So just because we crashed, we still need to be able to commit. So our solution here is going to be that each participant is going to have to keep track of all of the transactions that it's been involved in on some persistent storage, like on a disk, so that when this thing turns its sad face upside down and gets rebooted, oh, that didn't make it any better, and gets rebooted, it's going to be able to look back and say, aha, I was in the middle of this transaction, I voted yes. Did I hear an outcome? If I didn't hear an outcome, maybe we ask the coordinator what happened. Okay, so we're going to be doing some logging. Each machine, each participant is going to have to keep track of the stuff. Let's see another one. So we'll send out our prepare message, and we'll get back our responses. Maybe again, both vote yes. We saw what happened when one of the participants crashed at this point. What happens if the coordinator crashes? So our coordinator received the votes, but now it crashed. So again, let's see, what is it that we're trying to get here, right? Can this participant abort? Can this participant abort? No, right? Both guys said yes. We said the only way you can abort is if you hear the word abort back from the coordinator as long as you voted yes. So they're not able to do that. They're going to be stuck around waiting probably until the coordinator comes back. But when the coordinator comes back on, as long as it's doing this logging also and the coordinator knows all the responses that it got and how far it was in the protocol, when the coordinator turns its sad Mac face upside down and becomes a smiley Mac face, it's going to be able to come online, look back in its log and say, aha, I was in the middle of this transaction, we need to keep playing it out. Let's do another one. So we'll have our coordinator send out its normal first prepare message, and then we'll get back yes from one of the banks. And then maybe in the process of another response coming back, there's a network failure, and that message gets lost. So in this case, note that none of the participants are crashed, right? How many sad Macs do I have? I have 0 sad Macs. All of the machines are still working, but can we make progress? Do we have liveness? In this case, where the coordinator times out on waiting for a response. Well, we're lucky here in this case, because even though the coordinator hasn't heard back from one of its participants, we can come up with a safe solution here. And that safe solution is that the coordinator can always default to abort. So even though it heard a yes vote from this participant, and even though there was this yes vote that started coming across but got lost, the coordinator can always say abort because all that it has to do is send a message to each participant that says abort. And then we're done. Okay. Let's say another timeout case. So the coordinator sends a prepare message. What happens if this message now gets lost in the ether as it's being sent to one of the participants and the message is gone? So we saw what happens if the coordinator timed out on getting a response, but what happens if a participant times out while waiting for the prepare? Thankfully, this one has a safe answer also for what could happen, because at least as shown so far, none of the participants have voted yes, so it could be safe to abort. This guy can abort because he didn't hear prepare, so he didn't vote yes. Eventually, the coordinator is waiting to hear back, and it never hears back from that participant, and then the coordinator can decide to abort and send that message out. So what's key here is if we didn't vote yes, we can abort, and then we can rely on the coordinator eventually figuring out that things didn't happen, it can abort too. Let's see another one. So we send out our prepare messages and we get back both of our response messages. So we saw what happens if the prepare messages get lost. We saw what happens if the response messages get lost. What happens if the outcome message gets lost? So we have that final outcome going to those Duke and Duke guys, and then that message gets lost in delivery. So this is the case where one of the participants times out while waiting to hear the outcome of the transaction. And our problem is, can we understand, in this case, we had pretty nice answers for the rest of these timeout or crash cases, if there's some way that eventually this participant can determine what the outcome is. Well, let's consider what the possible final outcomes of the transaction might be, because remember that even though Duke and Duke voted yes, we don't know what the other participant voted, and maybe the coordinator timed out. We can't assume anything. So let's look at what the possible options are with the different votes. So one option is that the other participant voted yes and we voted no. So if that's the case, without knowing what this guy voted, we know that the outcome has to be abort because we know that we voted no. Similarly, if we both voted no, the outcome has to be abort. But if we, as Duke and Duke, voted yes, well, it could be the case that the other participant voted yes also, in which case the final result should be commit. But the other guy might have voted no also. So if the other guy voted no, the final outcome would be abort. So the reason why we make this table and look at it like this is because our world right now is looking only in here at this one participant. And the only information that we know is what we voted. But we still want to have some way to move forward, even though we don't know what the outcome of this transaction is. Does this participant have to wait around indefinitely to find out what the outcome is? Right? We already said some reasonable thing like, well, we'll wait for 5 seconds, we'll wait for 5 minutes, we'll wait for 5 hours, we'll wait overnight. I don't know, right? Some reasonable amount of time. That time has passed. So this fundamental problem that we have in this distributed agreement and distributed transactions is that all three of these people, coordinators, need to decide either commit or abort, commit or abort, commit or abort. And honestly, as system designers, we don't really care if it's commit or abort. The only thing that we have with our protocol is it needs to all be the same, right? All three of these players here, the coordinator and the two participants, they all need to agree on commit or abort. But now we're in this position where we're one of these participants. We didn't hear some message. We don't know what happened. Is the coordinator still out there? Has there been zombie apocalypse? But you know, that's not really the interest so much of the transaction processor. It just wants to know, should I do this transaction or not? So the solution is going to be here, as long as we voted no, then we know that the outcome will always be abort, right? Regardless of what any other participant said or what the coordinator saw or if the coordinator crashed, if I voted no, there's no way that this transaction could proceed. So if we vote no, we can abort safely. But if we vote yes, the only information that we know is that we voted yes. We don't know anything else. It could be the case that the other guys decided on commit, or it could be that the others decided on abort. And because of that, two-phase commit does not guarantee liveness. In the case of this kind of timeout, where we vote yes, but then don't find out what the final outcome is. We'll go through that again in a minute. All right. So what do we log? How do we do this recovery? And how do we formalize what the timeouts are? So if we want to be able to recover from one of those sad Mac faces, from having our machine crash, either our coordinator or one of our participants, then we need to log each change in the protocol. So that means we start out that we want to make a transaction. Then the transaction's being prepared, we send that message, and then we get back some votes, and then we find out whether it's committed or aborted. So for the participants, that's prepared, being uncertain, and then being either committed or aborted. And for the coordinator, that's being prepared, and then committed or aborted, and then done. So these messages are idempotent. Remember that buzzword? They can be repeated. So we can have multiple messages saying that the same transaction is committed. It doesn't hurt us. Our recovery then is going to depend on the kind of failure. So we're going to have recovery strategies for having that hard crash. And then we'll also have recovery strategies for having that timeout. So as you may have gathered from as we worked through those examples there, it's a little bit more straightforward and quick going through the crashes and the timeouts. So we'll go through the crashes first quick. And there is your obligatory Ripley hello. So what do we have to guarantee here? If the commit has been decided that this thing is committed, we can never back out, right? I said yes, or I heard the final word on commit. We cannot just get rid of it. So if we're the coordinator and we crash just after deciding to send the word out to everyone that we should commit, but not before we did it, then the coordinator must have logged and remembered that decision, and it's all right to replay it. So no problem for the coordinator to perhaps inadvertently send a duplicate commit message, because each commit message, each transaction had this transaction ID. So the coordinator is just going to say, hey, transaction 1 is committed. Hey, transaction 1's committed. Right? Maybe it's a nuisance. Maybe it's a little bit extra network traffic than we need, but it's not going to make something be wrong. If the participant had crashed just after giving its vote, like saying yes to commit, then it needs to remember this decision also. It needs to log that so that it can replay it. So each of the nodes are going to need to log their progress as they go through this protocol. So again, we'll just do this and overlay what's happening in terms of fault tolerance and recovery. So we start off our transaction, and we're going to log the fact that this transaction is starting and what its transaction ID is. Those prepare messages get sent out. Those get received on each client. The clients have to log that too. So the clients need to know that the transaction had been started by the coordinator. And we do our stuff. If we're able to commit, we do our work, and we vote. We send our responses back. The coordinator gets those responses. Each one of those responses is being logged also. And then when the final outcome is decided, the final outcome gets logged also, and then we send that out. Of course, then each one of the participants has to log those final outcomes too. So every phase of this protocol, everywhere where there's a chance for communication, those messages have to be logged. To do that recovery, once the machine gets rebooted, if the coordinator finds that a transaction was started but there was no final commit message that gets sent out. So that's the situation where we've got our multiple machines and we said prepare or maybe we even got back some votes. As long as the coordinator has not sent out a message that says commit, then it's safe to abort because no node will be able to decide to commit unless it hears commit from the transaction coordinator. And that's why it's really important that the coordinator has to log to its disk that message before it sends it. So if we don't see it, we can safely abort because we know no one else could have committed and everyone else will eventually abort too. That's fine too. A lot of this is really about kind of coming up with sane defaults so that in a bad case, everyone can kind of just go to the same place, abort. But if we do find that we sent that commit message, then we resend it and notify all the nodes, hey, I sent this, let's just make sure, so commit. It's idempotent, remember, so if we send it again, it's not going to cause any harm. If a participant finds no message that it ever sent about a transaction saying, yes, I would like to commit this, then it's safe for it to abort it. Because if that participant knows that it never voted yes, then it never could have been finally agreed on by everyone because at least one person didn't say yes, us, so it's safe to abort. And if we find that yes, okay message saying, yes, I'd like to vote for this, then the participant is going to replay that message, send that back to the coordinator, and keep going. At that point, the coordinator either sees that this transaction was committed or aborted, or it was waiting for that result, and then the coordinator either sends back that cached result or plays it through. So for crashes, we have this story, right? And the story is eventually a machine will come back up and we logged stuff and we can keep going. But what happens with timeouts? So we want to have some amount of liveness where the system will keep making progress and we can set some bound and say, by the end of the week, this transaction will be done, right? I mean, hopefully we're on computers and we mean like within milliseconds, this transaction is done. So those are the cases where we have the coordinator maybe timing out waiting for bank response, the bank timing out waiting for the coordinator's final outcome message. And now it's really important to note that it's really tempting to just say, oh, like this will never happen, right? But the causes for timeouts are really super realistic, right? Maybe your network is slow or congested or out. Maybe your hosts are overloaded. You don't have enough capacity. So just sometimes during the day, this stupid bank is running slowly and it's going to take longer. So here were, just to put it all in a few slides, what the different scenarios were and how and why we can go down each route. So if we're the coordinator and we time out while we're waiting to hear from some bank, if we're waiting to hear from the bank, let's just remember what the different phases of the protocol here, right? The coordinator sends prepare, and then we get back the vote, and then we send back out the outcome. So if the timeout happens at this point, then the coordinator has definitely not sent any message with a final outcome, right? It couldn't have said commit, so it's safe for us to abort. Note that this preserves correctness at the sacrifice of performance. And that's because maybe everyone else was going to vote to commit and it just took too long. But it still is correct because everyone will eventually agree on abort. Because if the coordinator decides to abort, it never sends a message that says commit. Everyone else will eventually abort too. It could even send the message abort. If either bank decided to commit, right, it was fine. They will eventually abort. If the coordinator waits times out hearing from a bank, this is fine. That nasty case came up when the bank doesn't hear back from the coordinator. Draw the same diagram, always. So we're talking now about having a timeout here. So we're one of the banks, we were told to prepare, we sent our vote in, and we haven't heard back yet what that outcome is. Let's get rid of that. We don't know. Commit, abort, who knows? So we said that if we voted no, then it's okay to abort. And it's okay for us to abort because nobody else could commit because they didn't hear us say yes. But if we voted yes, we cannot decide to abort. And the reason why we can't decide to abort is that maybe the other bank voted yes too. And maybe the coordinator even heard that. And maybe the coordinator already even sent out a message saying commit, and we just missed the message. So we definitely cannot abort. But we also can't commit because maybe the other bank did, as we just said, indeed vote yes. So do we have to make the bank wait indefinitely to find out what the outcome is? This might be unattractive if we don't guarantee that the protocol will eventually complete within some reasonable timeout. So there are some of these timeout problems we saw that we can solve with this guaranteed correctness, like if one bank voted no, but there also maybe are some corner cases where it'll work if a bank voted yes. So for instance, one thing we could do is the two banks could talk to each other. So even though we had our three lines here, we have our prepare and our vote. Let's make it shorter, P, V, V, and outcome. Even if that outcome never really gets all the way to this other participant over here, if this participant can talk to this one and just be like, hey, what's the outcome? And then it can share it back. So if the bank heard back commit or abort, then they can just do that. If the other bank didn't hear, and one of them voted no, then now we're a little bit better off because we knew as long as one person voted no, the decision is definitely abort. But if the other one voted yes, then there truly is not going to be any decision that's possible here. And this protocol will stall indefinitely if this message gets lost or delayed. So it's really important in two-phase commit, if we want to make sure that this has this nice liveness property, that these outcome messages are not going to be lost. So we saw with two-phase commit that we can solve a lot, but not all of the cases, by having the participants talk to each other or by being really tricky about thinking about reasoning through what these defaults are. If anyone ever aborted, anyone ever voted no, then we end up with this abort. But still see this, if the coordinator fails, doesn't get the outcome to everyone, then all of the nodes in the transaction are going to be stuck and they're going to stall. Can the coordinator fail? Like, absolutely, right? This is now going to be one special node that can never fail. And if it does, it'll take down our whole system. In the example that we just saw with the bank transactions, this was a transfer only between two banks. If we wanted to make some big transaction that included hundreds of different parties, maybe we'd have it set up so that if one of those parties failed, it could still move forward. But if that coordinator fails, the whole thing is going to get stuck and stalled. We'll come back to this idea of discuss amongst yourselves kind of transactions where different nodes talk to each other and try to coalesce on this final overall agreement about whether the transaction should be committed or not next lecture and over the next few weeks. So not to leave it on a terrifically bad note, though, about two-phase commit. So two-phase commit is guaranteeing safety, but not liveness. But there are good parts. Two-phase commit really doesn't require very many messages. Each transaction, to start it and then to get to it completed, requires just a few exchanges, right? We have this prepare, and then we have a vote, and then we have the outcome. So talking about latency can be important, because remember that we're talking about having these timeouts in terms of how long we wait for this response before we give up. So if this timeout is 3 sec, then completing this protocol could take at most 3 seconds for each message for 9 seconds total. If we had a more complex protocol that did guarantee this liveness, but maybe required 10 sets of messages instead of 3, then it would take 30 seconds, perhaps in the worst case. Could be 3 times slower. Ooh, I don't know. Maybe speed could start to matter in some cases. Or maybe fault tolerance is going to be more important in others. So these are the kinds of trade-offs that we're going to start to look throughout the rest of the class. We're going to see maybe something is faster in one way, but to recover might be really slow. Or maybe there are these cases where under a specific kind of failure, the system falls apart. And what I want to make sure that you get out of this class is to see how those design choices can be made and how they impact a bigger system that you're building between this trade-off of fault tolerance and performance. So good luck on homework 3, and I will see you all on Wednesday. Have a good start to your week.